Hello students, welcome to the class. So in the previous class we have discussed about atomic radius. What is atomic radius? So it is the distance from the center of the nucleus when we consider a single atom and try to define it. It is the distance from the center of the nucleus to the outermost shell where there is electron is present. So this distance we call it as atomic radius or atomic size. But sometimes what happens, measuring this distance becomes impossible because we cannot predict the electron position exactly. Therefore, we define it as considering a molecule of two atoms, similar atoms, say H2 molecule I'm considering. This is one hydrogen atom, another hydrogen atom. The internuclear distance, the distance between the two nuclei is taken. So it is called internuclear distance. When you take half of the internuclear distance, it becomes what? Half of the internuclear distance becomes the atomic radius. It becomes the atomic radius. So this is how we define atomic radius. Okay. Apart from that, we have seen types of radius, atomic radii. Yes, covalent radius. Covalent radius comes if the atoms are covalently bonded to each other. That is, when there is sharing of the electrons. Purely there is a single covalent bond. Covalent radius comes into context. Ionic radius, effective distance from the nucleus of an ion up to which it has an influence on the ionic bond. Then we have van der Waals radius and metallic radius. As we have already discussed, covalent radius means what? When the two like atoms, okay, when the two like atoms are bonded by a covalent bond. Covalent bond is formed by sharing of electrons. We'll discuss it in chemical bonding topic. So when this case is there, then how do we determine the covalent radius? Covalent radius is written as RC, covalent radius. That is nothing but the internuclear distance between the two covalently bonded atoms divided by 2. Or you can write it as the radius of one covalently bonded atom plus radius of another divided by 2. So this is nothing but covalently bonded radius. But if the two atoms are unlike, if the bond is between two unlike atoms, if there is a covalent bond between two unlike atoms, then in case of that, how do we define covalent radius? We define it as radius of one particular atom plus radius of another atom, because both radii will be different. For example, if you take HCl, so one is hydrogen, another one is Cl. That time both the radii are not same. Minus 0.09 x of A minus x of B. This is how we determine the covalent radius. X of A stands for electronegativity of atom A. X of B stands for electronegativity of atom B. Yes, this relation was given by Stevenson. It was being given by Stevenson. This is how we determine the covalent radius. Okay. Ionic radius, it is from the distance from the nucleus of an atom to the outermost where the availability of electron is there in the electron cloud. Only in first case, atomic radius, we'll talk about atom. Here we'll be talking about the ion. We'll be discussing about the ion. So effective distance from the nucleus of an ion up to which it has its influence in the electron cloud. We say ionic radius. Okay. Then van der Waals radius, metallic radius, it is for the metal atoms. When the two metal atoms are held together, same. Two metal atoms are held together, sodium atoms, half the internuclear distance. So if this is atom 1, this is atom 2. So the radius, metallic radius is equal to Ra plus Ra divided by 2. Radius of one metallic atom, radius of another metallic atom divided by 2. Or I can write it as D by 2. Internuclear distance divided by 2. But when it comes to the case of van der Waals radius, van der Waals radius. So how do we define radius of van der Waals radius? It is half of the distance between the nuclei of two adjacent atoms belonging to neighboring molecules. Now let me say I have two molecules like this. One molecule with two atoms, another molecule with two atoms. This is what half of the internuclear distance is atomic radius. But when I say van der Waals radius, I will consider the internuclear distance between adjacent atoms of neighboring molecules. Adjacent atoms of neighboring molecules. So this internuclear distance divided by 2 I will get van der Waals radius. I'll get van der Waals radius. Therefore, when I compare all of them, covalent radius is always smaller than van der Waals radius. Covalent radius is always smaller than van der Waals radius. Not only that, covalent radius is smaller than metallic radius. Covalent radius is smaller than metallic. So totally we say covalent radius is smaller than metallic radius, which is smaller than van der Waals radius. Now what is the reason? Why covalent radius is smaller than van der Waals radius? This is because in the formation of a bond, the two atoms have to come closer. In case of covalent radius, this is how we define covalent radius. So this bond is formed when the two atoms come closer. So when they come close to each other, yes, when they come close to each other, their distance becomes less. Okay. In case of van der Waals radius is mainly found in noble gases because noble gases are monoatomic molecules. They are monoatomic molecules. That means they are molecules of one atom only. So this is one molecule, this is another molecule. So that time, how do I measure the distance? And there exists van der Waals forces of attraction. Forces of attraction. Van der Waals force of attraction. So when I measure half distance between the two nuclei of neighboring atoms, and when I take half of it, it becomes van der Waals radius. Van der Waals radius. Yes. So noble gases ordinarily do not form any bonds. In the crystal of noble gases, no chemical forces are operating between the atoms. Hence, van der Waals forces are the only attractive forces in these cases. Yes. So in other words, van der Waals radius constitutes what? It is the atomic radii of the noble gases. And since van der Waals radii are larger than covalent radii, atomic radii of noble gases, I can conclude atomic radii of noble gases are largest in their respective periods. Yes, we know in their respective periods. Okay. So this is consideration. Why? Because van der Waals radius is large. See, van der Waals radius is measured like this. Atomic radius is measured like this. Therefore, we conclude with this particular explanation. Now, variation of the atomic radius in the periodic table. When we speak about variation, it is along the period or across the period, moving from left to right and down the group. Along the period, the atomic radii of the elements generally decreases from left to right. And there are certain exceptions. Within a period, protons are added to the nucleus as electrons are being added to the same principal energy level. Okay, let us try to understand. I'll make things clearer and then we'll read out. So along the period means what? Across the period, or you can say along the period. Doesn't make any difference. Along the period means when we are moving from, in the periodic table, when we are moving from left to right. Yes, when we are moving from left to right, like this. Yes, when I say across the period, it is understood like this. And when I say down the group, I am moving from top to bottom. Top to bottom, like this. Understanding? Okay. So across the period, atomic size decreases as I move from group 1 to group 17. Group 18 are studied separately. You know, in any group, in any period, group 18 elements have the largest. Noble gases have largest atomic size. So I'm speaking only from groups 1 to group 17. When I move from top to bottom, yes, the atomic size increases. That means when I'm moving from left to right, if this is the atomic size of first element, the second element atomic size will be so much. The next element atomic size might be so much. Then next might be so much. Yes, I'm just showing you all. Yeah. Fluorine. Yes. So if I say this is lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. Like this, when I move across the period, this is the second period I'm saying, the atomic size decreases. And when I move down the group, So down the group means what? First is lithium. So let me say lithium is so much. Next element will have so much size. After that, it will have so much size and it goes on increasing. So if this is lithium, below lithium is what? Sodium. Below sodium is what? Potassium. Atomic size goes on increasing. Now, why is this case? Okay, why atomic size decreases across the period? So when you move across the period, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. We have to consider only these, okay, up to group 17 only. So here if you see configuration 1s2, 2s1. 2p is there but it is 0. For beryllium 1s2, 2s2. 2p is there but it is 0 because there are only 4 electrons. Boron 1s2, 2s2, 2p 1. Carbon 1s2, 2s2, 2p 2. Nitrogen 1s2, 2s2, 2p 3. Oxygen 1s2, 2s2, 2p 4. Fluorine 1s2, 2s2, 2p 5. So if you carefully observe here students, the outermost shell is this. In all the cases, in the second period means what? The electrons are entering into the second shell. Yes. Third period means what? The electrons are entering, last electron is entering into third period, third shell. That defines period number determines what? Period number determines the number of shells. If period number is 1, there is only one shell for the elements. Period number 2, so this is second period. How many shells are there? Each element has two shells. Period 3, each element will have three shells. So what does this mean? So if you see here, when you move from left to right in the periodic table, what is happening is atomic number is increasing, correct? Atomic number is increasing. This is first point what we are observing. So what happens when atomic number increases? Z is atomic number, right? Atomic number is increasing. As atomic number increases, number of protons increase, correct? Increase. And you say, of course, teacher, if protons are increasing, electrons also increase. Yes. If there is from 3 to 4, that means there is one proton increase, there will one electron also increases. Okay, number of electrons also increase, but this is not my case. What I want to study about electrons is, observe. Here, the last electron is 1. It is entering into second shell. Here, the last electron is entering into second shell. Here, the last electron, it is entering into second shell only. These are subshells. Last electron, second shell only. Last electron, second shell. So, in a given period, the last electron, this is the next observation. Last electron means what? Differentiating electron. Differentiating electron is entering into same shell, correct? It is entering into same shell. There is no new shell created. It is entering into same shell. Are you all understanding? So here, if this is, yes. Okay. So what I say here is, you can see here, this is nucleus. If this is the atom of lithium, here there are two electrons and electron is here. Second case, okay, beryllium same. So if this is beryllium, there will be one more electron here. Boron, let me show you. So this is one. Okay. Understanding. So in this case, in case of boron, if this is a element of atom of boron, two electrons are here. Here, how many are there? The two electrons of S and one electron. So it is getting added to the same shell. This is first observation. Okay. So differentiating electron is entering into the same shell. Next observation is, okay, please try to understand here. Here, I'm just trying to make you all understand by drawing bigger diagram. Okay. Fine. So as atomic number increases, number of protons increase. Yes, number of protons here, they increase. So number of protons increase. Number of protons are increasing means what? Positive charge is increasing. And where is that positive charge present? It is present in the nucleus. Therefore, the positive charge of the nucleus is called nuclear charge. Correct? So as the atomic number increases, nuclear charge increases. Correct? Nuclear charge increases. So first observation. Nuclear charge is increasing and number of electrons are also increasing. Yes. But what happens? Since the electrons are added to the same shell, the increasing nuclear charge, successive increase of the nuclear charge is there. This increased nuclear charge, it will attract the electrons more strongly towards itself. It will attract the electrons more strongly towards itself. Therefore, the size of the atom happens what? The size of the atom decreases. The size of the atom decreases. It will pull the electrons more strongly. It will pull the electrons as the nuclear charge increases. It will pull the electrons more strongly towards itself. Therefore, the atomic size decreases when you move from left to right in the periodic table. So how do I explain this? So what happens? Due to successive increase, can you see here? Due to successive increase in the nuclear charge across, when you move from left to right, nuclear charge is increasing and the electron is being added to the same shell. So there is no addition of the new shells without the addition of new shell. So in each element of a given period, the last electron is added to the same shell. Yes. So the increased nuclear charge, it will attract the electrons more strongly towards the nucleus. It will attract the electrons more strongly towards the nucleus and thus decreases the size of the atoms. Thus decreases the size of the atoms. I am saying this is only till group 17 elements. What about group 18 elements then? In case of noble gases, that is group 18 elements, what is atomic radii? Atomic radius is nothing but van der Waals radius. Yes, and they are naturally higher than the covalent radius. Therefore, that is studied differently. Yes, they are studied differently. So right now you try to understand, when you move from left to right in the periodic table, the atomic size decreases. The atomic size decreases. Okay. Now, when you move down the group, let us consider examples again. Lithium, atomic number 3. Below lithium is sodium, atomic number 11. Below sodium is potassium, atomic number 19. So see here, 1s2, 2s1. 1s2, 2s2, 2p6, 3s1. 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Okay, what is happening? In case of lithium, there are 2 shells. In case of sodium, there are 3 shells. In case of potassium, there are 4 shells. So, as you move down the group, so there are 2 shells in case of lithium. Then sodium. There are 3 shells in case of sodium. Potassium. Can you see this? So in case of lithium, this is 1s, this is 2s. In case of sodium, 1s, 2s, 2p, and this is 3s. In case of potassium, this is 1s, 2s, 2p, 3s, 3p, and this is 4s. So what is happening? No doubt, as you move down the group, atomic number is increasing. Z is increasing. So nuclear charge also increases. But in case when you move down the group, the electron is added in a new shell. It is added in new shell. So when the electron is added in the new shell, what happens? As the energy level increases, the orbital size also increases. We have studied in principal quantum number. As n increases, the size of the orbitals also increase. And therefore, what we say, the creation of new cells outweighs the nuclear charge. So when we move down the group, yes, when we move down the group, what happens? The increase in the size on descending down the group, on moving down the group, it is due to addition of, extra shell. Addition of extra shell. And this extra shell, it outweighs the increased nuclear charge. It outweighs the increased nuclear charge. Therefore, on moving down the group, the atomic size, it increases. So we can say, only I am speaking from group 1 to 17, okay, not about 18. So considering all these groups and periods coming under these groups, I can conclude saying helium. Okay, let us consider 18 also, because helium comes into context. Helium is the smallest atom. Neon and all, they have got large size. Francium. Francium is the largest atom. Helium is the smallest atom and francium is the largest atom. Yes? Okay. So explanation. Within a period, protons are added to the nucleus as electrons are being added to the same principal energy level, that is shell. These electrons are gradually pulled closer to the nucleus because of its increased positive charge. What is positive charge? It is nothing but nuclear charge. Since the force of attraction between the nuclei and the electrons increases, the size of the atom decreases. The effect lessens as you move further to the right of the period because electron-electron repulsions that would otherwise cause atoms size to increase. You can see here. Lithium, beryllium, there is drastic increase. It is in picometers, okay? So around 40, then 88 picometers, carbon 77, 74. See, there is a very less decrease after that. Yes, because electron-electron repulsion also will be there. Shielding effect comes into context. Similarly for second period elements, when you move from left to right. So if you plot a graph of atomic radius in picometers versus atomic number, from lithium, beryllium, when you move from left to right, the atomic size gradually decreases. Atomic size decreases. In a group, the atomic radii of the elements in every group of the periodic table increases as you move downwards. As the atomic number increases, there is again increase in the positive nuclear charge. Yes. However, there is also an increase in the number of occupied principal energy levels. So number of shells increase. Higher principal energy levels consist of orbitals which are larger in size. Yes, as the n value increases, the orbitals in those particular energy levels, they will have larger size than the orbitals from lower energy levels. The effect of greater number of energy levels outweighs the increase in the nuclear charge, and so atomic radius increases down the group. Atomic radius increases down the group. You can see when you move from lithium, sodium, potassium, rubidium, cesium, there is increase in the atomic radius. Even group 17, there is increase in the atomic radius, and this is the graph. This is for group 1 elements and this is for group 17 elements. So when you move down the group, there is increase in the atomic radius. Please try to remember this. Across the period, atomic size decreases and down the group atomic size increases. This is how we can explain pictorially. Can you see here? When you move across the period from left to right, atomic size is decreasing. See here, atomic size is decreasing. This is second period, third period, atomic size is decreasing. Fourth period, atomic size is decreasing. Fifth period, atomic size is decreasing. Seventh period, atomic size is decreasing. When you move from top to bottom, lithium, sodium, potassium, rubidium, cesium, atomic size is increasing. So atomic size goes on increasing. Yes. So across the period, atomic size decreases and down the group, atomic size increases. Atomic size increases. Ionic radius. Okay, what is ionic radius? So we have discussed what is an ionic radius, effective distance from the nucleus of an ion up to which it has its influence on its electron cloud. Okay, ionic radius comes into context when we speak about ions. When we talk about ions. Okay, so what are ions? Ions are nothing but they are charged species. Charged species formed by loss or gain of one or more electrons. Yes. For example, I'll take example. We know that metals, let me make this point very clear. They are electropositive. They tend to lose electrons. Yes. Non-metals, they are electronegative in nature. They tend to gain electrons. Okay. When I consider example, yes, suppose I have an metal. If it loses electron, if it loses one electron, so it will have positive charge and the ion formed is called cation. So metals tend to lose electrons to form cations. Depending upon how many electrons are lost, there are types. You say monovalent cation, loss of one electron, divalent cation, loss of two electrons, trivalent cation, loss of three electrons, and so on. Polyvalent cation, loss of four or more electrons, like that. If you have a non-metal, say let me represent it as E, it will gain electrons and form negatively charged ions, which are called anions. And there also you have types, same types you have. Monovalent anion, divalent anion, trivalent, polyvalent. We denote it. Monovalent cation is M plus, divalent cation is M plus 2, trivalent cation is M plus 3, polyvalent and so on. M plus N we represent. Anion, monovalent anion M minus 1, divalent anion minus 2, trivalent minus 3, polyvalent minus N. Okay. Here, consider an example. Okay. Atomic number is 11. Configuration 1s2, 2s2, 2p, 6, 3s1. Okay. So when sodium atom loses one electron, so one electron comes out, it will form what? A cation. And I've told you how it forms a cation. Here there are 11 protons, 11 electrons. When one electron is lost, 11 protons only will be there, 10 electrons will be there, correct? So number of protons is more, positive charge. By how many units more? 1 unit, therefore plus 1. So it is a monovalent cation, or you can say unipositive cation. Okay. If I consider fluorine, atomic number is 9. Okay, what happens to the atomic mass number here? 1s2, 2s2, 2p6. Sorry, not mass number, electronic configuration of this cation will be so much. Fluorine 1s2, 2s2, 2p5. When fluorine gains one electron, it forms F minus 1. See, in case of neutral atom, 9 protons, 9 electrons. Here there are 9 protons, but number of electrons are more, so 10 electrons. So which charge is more? Negative charge is more. By how much? By 1 unit. So it forms an anion. Okay. Configuration coming to 1s2, 2s2, 2p6. Okay. Let us look at the sizes now. So a cation is formed by loss of one or more electrons. Anion is formed by gain of one or more electrons. Now if I want to draw sodium atom, how many shells are there? There are 3 shells. Let me represent. Okay, I'll represent sodium ion this side. It is having how many shells? It is having only 2 shells. Correct? Understanding what I'm trying to say? This is nucleus. This is nucleus. So this is my neutral atom sodium. So here there are 2 electrons. Here there are 2 and 1, 2, 3, 4, 5, 6. Subshell let us consider. Here there was 1 electron in the neutral atom. When the electron was lost, so when the electron was lost, this shell, entirely shell went off, right? So I got it as Na plus. Understanding? What happened to the size of the atom when the electron was lost? That means when a cation is formed from the neutral atom, what happens to the size? The atomic size decreases. Therefore, I say, yes, a cation is always smaller than its atom. Yes, not any other atom, its atom only. So if you are considering sodium, sodium ion will be smaller than sodium atom. Yes. One more example. Now you may say, teacher, what if there is no decrease in the shell itself? The example is, I will write the example. Say nitrogen. Yes, atomic number is 7. So first shell 2 electrons, second shell 5 electrons. When nitrogen loses 1 electron, it forms, okay, nitrogen doesn't come into context, so it cannot lose electron, it will gain electron, right? Okay, let us consider boron. Atomic number is 5, 2 and 3. If boron loses 1 electron, it forms B plus. So here it becomes 2, 2. Understanding? So here, unlike in case of sodium, in case of boron, there are only 2 shells, and even when the electron is lost, there are the same number of shells. Yes or no? Can you see here? Understanding? So this is boron atom, this is boron ion. So in this case, there were 2 electrons here, 3 electrons here. In this case, 2 electrons here, and there are 2 electrons only here because 1 electron is lost. But still, this cation will have smaller size. So this condition is true for any cation. A cation is always smaller than its neutral atom. So if this is neutral atom, the cation is always smaller than its neutral atom. Why? Why it is always smaller than its neutral atom? Now the reason. In this case, if I consider same example, nuclear charge has how many protons? 5 protons. Here also there are 5 protons. So here 5 protons, 5 electrons, 5 protons, 4 electrons. Understanding? So this nuclear charge, attraction of this nuclear charge, in the case of boron atom, it is distributed to 5 electrons. It is distributed to 5 electrons. But in case of boron ion, the nuclear charge with 5 protons, it is distributed to only 4 electrons. So what happens, since the number of electrons is less, number of electrons decrease, the nuclear attraction on the remaining electrons increase. Nuclear attraction on remaining electrons increase. So when the nuclear attraction on the remaining electrons increase, it will pull the electrons more closer towards the nucleus. Therefore, it decreases the atomic size. Therefore, we say a cation is always smaller than its neutral atom. So if I have cations like this, M plus 2, that means loss of 2 electrons. So let me say I have an atom with 10 electrons. When it loses 1 electron, it becomes M plus. So 10 electrons, when it loses 2 electrons, it becomes M plus 2. So here 2 electrons are less. In this case also 10 protons are there. Here also 10 protons are there. Here also 10 protons. Here also 10 protons. But in this case, the nuclear charge is distributed to 10 electrons. Here, the nuclear charge is distributed only to 9 electrons because 1 electron is less. In this case, the nuclear charge is distributed only to 8 electrons because 2 electrons are less. Understanding? So, nuclear attraction in this case becomes more on the 8 electrons and it will be pulled more strongly. So, if you see the atomic size, if this is the neutral atom, this will be the size of positive ion. This will be the size of bipositive ion. Understanding? So if this is neutral atom, this will be the size of positive ion, unipositive ion, that is cation, and this will be the size of unipositive, bipositive cation. Yes. So as a cation is always smaller than its atom, as the what you say, as the charge on the cation increases, the atomic size decreases. So I conclude here saying a cation is always smaller than its atom only. Okay, you cannot take a sodium cation and compare it with lithium cation. No. Then as charge on cation increases, the size decreases. Do remember. Yes, as the size on cation increases, as the charge on cation increases, the size decreases. So if I say I have magnesium atom, I have magnesium cation, unipositive cation, I have magnesium dipositive cation. Arrange them in the increasing order. So which comes first? This is first. This size is less. It is less than this. It is less than this. So this will be bigger. This will be bit smaller and it will be still smaller. Understanding? So a cation is always smaller than its atom. As the charge on cation increases, the size decreases. What about anion now? Okay, oxygen. Atomic number is 8. 1s2, 2s2, 2p, 4. Correct? Okay, let us see now. So oxygen, it is having, let us represent. How many shells it is having? It is having 2 shells. And this is the nucleus. Fine. So this is the nucleus with 8 protons. And here are the electrons. 2 electrons here. 1, 2, 3, 4, 5, 6 electrons in the outermost shell. Oxygen is a non-metal. It will tend to gain electrons. So oxygen will gain 1 electron and forms O minus ion. Okay. Where the electron will go? It will go to this shell only. Yes. Because this shell is having still vacancies, right? Maximum electrons is for this is, so it becomes, I'll tell you what, it becomes 1s2, 2s2, 2p4 it was, now it has gained 1 electron, it will become 2p5. So is the number of shells increasing? No. The number of shells is not increasing. So it is remaining same. Correct? Okay. So this is the nucleus. Here there were 2 electrons. Here earlier 6 electrons were there and one more electron has become 6 electrons outermost shell. Now one more electron is more. Now if this O minus gains one more electron, what it becomes? O minus 2. Correct? 1s2, 2s2, 2p6. So how do we draw it? Is it going to the new shell? No. It is on the same shell. Correct? Okay. So here 2, 4 and 1 electron is added. Here there were 2 electrons. This is nucleus. And here there were 2s2, 2p4 electrons, 1 electron and 2 electrons are added. So it is 2p6. 1, 2, 3, 4, 5, 6, 7, 8. So 2, 2, 8. So if you observe, when an anion is formed, it is formed by how? It is formed by gain of electrons. Gain of electrons. So here in this case, oxygen, it is atomic number 8 means it is having 8 protons and 8 electrons. So this proton charge, it is distributed to 8 electrons, correct? It is distributed to 8 electrons. But when an ion is formed, still proton number is 8, but the number of electrons is increased to 9. So this nuclear charge now has to get distributed to 9 electrons, which was earlier getting distributed to 8 electrons. Therefore, the individual electron will experience less nuclear attraction. And even since a new electron is added, there will be electron-electron repulsion. There is electron-electron repulsion and there is reduced nuclear charge. Correct? Because now this 8 proton nuclear charge has to be distributed to 9 electrons, which was earlier distributed to 8 electrons. So due to which what happens? The atom, when repulsion is there, the outermost shell enlarges. Therefore, the size increases. Now with one more electron more. Here there are 8 protons in O2 minus. Now here how many electrons are there? 10 electrons. That means this charge has to be distributed to 10 electrons. Again, nuclear charge gets reduced on individual electron and there is also electron-electron repulsion. Therefore, the size of the atom still increases. Understanding? Therefore, we say an anion is always larger than its neutral atom. So when you consider an anion, its size is always larger. So if this is the size of oxygen atom, then O2 minus will have this size. O minus will have this size. O2 minus will have this size. Understanding? So if this is oxygen, O minus will have so much size, O minus 2 will have so much size, because in this case number as anion is created, number of electrons increase. As number of electrons increase, there is electron electron repulsion, and the nuclear charge per electron gets reduced, decreased. Therefore, they are pushed away, the shells are pushed away, which leads to increase in the ionic size. So if I tell you I minus or I plus, so which is having smallest size here? The smallest size is I plus. Then comes I, neutral atom. Then comes I minus. Out of O minus, O minus 2, which is having smallest size. O has a smallest size. Then comes O minus, and then comes O minus 2. If I give you, there is let me say, this is not possible. If I mention O plus, then O, then O minus, then O minus, to arrange them in the increasing order. So smallest size is for O plus. Then comes O, oxygen. Then comes oxygen anion, uni-negative anion, then bi-negative anion. This is how. Cation is always smaller, anion is always larger than its neutral atom. And as the number of charge and as the charge on anion increases, as charge on anion increases, becomes more negative, more and more negative at ionic size increases. Ionic size increases. In case of cation, as it increases, ionic size decreases. Ionic size decreases. Right? So the removal of an electron from an atom results in the formation of cation. The radius of cation is always smaller than that of its atom. Gain of an electron leads to an anion. The radius of anion is always larger than that of atom. Therefore, we say a cation is always smaller than its neutral atom, and anion is always larger than its neutral atom. So here is the explanation. Yes, ions are formed when atom loses or gains electrons. When an atom loses an electron, it forms a cation, and when it gains electrons, it becomes anion. Metals usually form cations, non-metals usually form anions. The atomic size of the cation will be smaller than that of the parent atom. An anion is relatively larger than its parent atom. This is because when an atom gains electron, the total number of electrons increase. This is about anion, which tends to create more repulsion between electrons and thus overshadows the net effective charge. Example, radius of potassium 243 picometers. Potassium ion is 138 picometers. So potassium ion is what type of ion? So radius of potassium is 243 picometers and that of potassium ion is 138. So cations are always smaller than their neutral atoms. Correct? Similarly, if you consider anions, the anions are always larger than the neutral ions. Okay. Isoelectronic species. So what are isoelectronic species? In our one of the classes only we have discussed, previous classes we have discussed what are isoelectronic ions. Yes, what are isoelectronic ions? Some atoms and ions which contain same number of electrons, we call them as isoelectronic species or isoelectronic ions. Isoelectronic species, or you can call them isoelectronic ions. For example, they have given the examples. O2 minus, F minus, Na plus, Mg plus 2 have same number of electrons. We have verified it once. We have discussed in one of our videos. So here, if you consider, what I'll consider is Na, Mg, then fluorine, oxygen, nitrogen. Atomic number is 11, 12, 9, 8, 7. So if you see here there are 11 electrons, 12 electrons, 9 electrons, 8 electrons and 7 electrons. If Na plus is there, that means what? Loss of 1 electron. So 11 minus 1 becomes 10 electrons. Mg plus 2. There are 12 electrons. Mg plus 2 means loss of 2 electrons. So 12 minus 2 is again 10 electrons. F, fluorine minus, if I consider. Fluorine has 9 electrons. Minus means gain of 1 electron. So there will be 10 electrons. O2 minus, if I consider. Oxygen, there are 8 electrons. Minus 2 means plus 2. There are again 10 electrons. Nitrogen minus 3, if I write. 7 electrons plus 3 becomes, so minus 3 means what? Gain of 3 electrons. It becomes 10 electrons. Okay. So here, all of these ions, though they belong to different atoms, atomic number is different, mass number is different, number of neutrons is different, but what is same? They have same number of electrons. And such ions are called isoelectronic ions. They are called isoelectronic ions. Now see, this is what we know. What if you consider the radius in isoelectronic species? Yes, their radii would be different because of their different nuclear charges. Yes or no? Sodium nuclear charges, 11 protons are there. The cation with greater positive charge will have what size? If there is a cation with greater positive charge, let me say I have ions like this. M plus 1 is there, M plus 2 is there, M plus 3 is there. Then there is an element M minus 1, M minus 2, M minus 3. Yes, let us say these are the different ions. Okay, okay, let me take it like this. Let me consider these ions only. Na plus, Mg plus 2, even you consider Al plus 3, aluminium, 13 atomic number, 13 electrons are there, plus 3 means loss of 3 electrons, it will have 10 electrons only. Then I have F minus, O minus 2, then I have N minus 3. Correct? These were the things which I considered. All of them have got 10 electrons. Therefore, they are called isoelectronic species. The cation with the greater positive charge will have smaller radius. The cation with greater positive charge will have smaller radius. So cation with greater positive charge, we have discussed, will have smaller radius. Why? Because as the positive charge increases, that means more number of electrons are lost. So attraction of the nucleus on the remaining electrons will increase. Anions with greater negative charge, anions with greater negative charge will have larger radius. Yes, because greater negative charge on anions means what? Gain of more electrons. Yes, when more electrons are gained, there is electron-electron repulsion that will make the anion to expand. Yes, so here, if you consider these two criteria, can you write the order for all these isoelectronic species? So which will be smallest? Al plus 3 will be smallest. So it will have smallest size, ionic size. Then comes what? Mg plus 2. Then comes Na plus. Then comes smallest one, F minus. Then comes O minus 2. And then comes N minus 3. Yes, this is the atomic ionic radii in case of isoelectronic species. So when I speak about atomic radius, when I speak about atomic radius, so if I say I'm talking about this periodic table, then as you move down the group, what happens to the atomic radius? Atomic radius increases. Yes, as you move from left to right in the periodic table, what happens to the atomic radius? Atomic radius is nothing but atomic size. It decreases. It decreases. Yes. So this is how we show the atomic radii. This is how, atomic radius. It is shown like this. Okay. So this is about the atomic radius or ionic radius or the radii of the isoelectronic species. Radii of the isoelectronic species. Yes. So both O2 minus Mg plus 2 have 10 electrons, but they don't have same ionic radius, as the effective nuclear charge in both of them is different. The radius of cation will be smaller than that of anion, as cation will have greater positive charge, that is number of protons. So it will attract the electrons in the outermost shell with greater force and hence the smaller size. In isoelectronic ions, the value of ionic radius decreases with increase in the atomic number. Within the series of isoelectronic ions, as the atomic number or nuclear charge increases, the atomic attractive forces between the nucleus and same number of electrons also increase. This results in the decrease of the ionic radius. So you can see here, aluminium smallest, magnesium, sodium, neon, fluorine, oxygen, and then nitrogen. Yes, so positive ions that have more protons would be smaller. Increase in the size from most positive to most negative, most positive to most negative. This happens in isoelectronic ions. So questions are mostly asked on isoelectronic ions. So I hope this point is clear. Moving to the next one, that is ionization enthalpy. Ionization enthalpy, which is also called as ionization energy. So what do we mean by ionization energy? Energy required to ionize something. Okay, what we are ionizing? Getting something into ions. When something means what? It is atom. When atom becomes ion, when it loses electron, it becomes ion, or when it gains electron, it becomes ion. Ionization energy means what? Or ionization enthalpy means what? It is the minimum amount of energy required to remove an electron from isolated gaseous atom in its ground state. So minimum amount of energy required to remove an electron. Suppose I have an atom, say I have an atom of sodium. Yes, atomic number is 11. I'm repeating it, 1s2, 2s2, 2p6, 3s1. Always remember the electron will be removed. Electron will be removed or added to valence shell only. Yes, not any other inner shells. Whatever reaction occurs, it is only because of valence shell. Therefore, we speak about the configuration of the valence shell only. Remaining inner core shells have nothing to do with. They may only cause repulsion to the outermost shell. That's it. Okay. So sodium, I want to remove this electron from sodium. So I cannot just say electron come out. Yeah. I need to put some energy. Let me say I have put some energy. Yes. So this energy is sufficient to get this electron out. So when electron comes out of that sodium, it becomes ion with +1 charge. So this is 1s2, 2s2, 2p6. So this energy which is required, minimum energy which is required to remove the electron from a neutral gaseous atom is called ionization energy. So you are creating an ion, yes or no? That is called ionization energy. Therefore, I can represent it as, suppose I have a neutral atom, gaseous atom. It should be gaseous, okay? When I supply it certain energy, minimum energy called ionization energy, electron comes out of it and forms a positive ion. So electron is lost. Yes, suppose I have this unipositive ion, I'll put some more energy, then what happens? The second electron comes out of it. It becomes M plus 2. Understanding? Or I will represent it here. So neutral atom, you put some energy, ionization energy, electron comes out of it. Correct? You take this metal ion and you put certain energy, minimum energy, remove the next electron. One more electron comes out, so plus 1 becomes plus 2, one electron comes out. You take plus 2, put certain energy, one more electron comes out, so plus 2 becomes what? Plus 3, and here one electron comes out. These are next nothing but the energies stepwise to remove first, second, third electrons. So the minimum energy required to remove the first electron from the valence shell is called first ionization energy. Minimum energy required to remove the second electron from the valence shell is called second ionization energy. And minimum energy required to remove the third electron from valence shell is called third ionization energy, and so on. Yes, therefore I can say first ionization energy, second ionization energy, third ionization energy, fourth ionization energy. These are all what? They are all successive ionization energies required to remove the next successive electrons. Right? So the energy required to remove the electron from the outermost shell is called ionization energy. And remember, when I talk about successive ionization energies, always remember the higher ionization energies are very much more than the lower. So I can write it like this. That means how much energy I require to remove the first electron from the outermost shell. When you compare it to the energy required to remove second electron, the energy required to remove second electron is more than first. The energy required to remove third electron is more than second, and so on. Yes, please do remember this. Now the question arises, why? Let me make this explanation. Suppose we have, say, element sodium. Sodium, it is 2, 11, right? 6 and 1. One more example I will take, magnesium. It is 2, 6, 2. Here I will take aluminium. 2, 6, 3. 13 6, 8. No. Sodium 11. So it is 2, 8, 1. Here magnesium 2, 8, 2. Aluminium 2, 8, 3. 1s2, 2s2, 2p6. So 8. Right? Okay. When you remove one electron, suppose you have given ionization energy, first ionization energy, and you have removed one electron. So it becomes Na plus. One electron has come out. So its configuration is 2, 8. So Na plus. If I want to remove one more electron, I have to put second ionization energy. Now, removing the electron from sodium ion is very difficult, because if you see here, outermost shell is having 8 electrons. Like noble gases, if any element or its ion has got 8 electrons in its outermost shell, it becomes very stable. And you are trying to remove the electron from the stable configuration. Therefore, what happens? To make it Na plus 2. Yes, to make it 2, 7 now. Therefore, in case of sodium, I can say the second ionization energy is 2 very much than the first ionization energy. In general, what I want to make you all understand is, when you have an atom of certain electrons, say n electrons are there. Suppose you supply first ionization energy, and you remove the electrons, one electron is lost. So n minus 1 electrons have remained now. Yes. If there are n electrons in an atom, there will be n protons. But when you apply ionization energy, one electron gets lost. One electron comes out. But the number of protons is still more. So when first ionization energy is applied to remove the electron, as you go on removing the electrons, number of electrons decrease. When number of electrons decrease, nuclear attraction on remaining electrons increases. Nuclear attraction on remaining electrons increases. So similarly, if you want to remove next electron, the nuclear attraction will be more. Therefore, you need to put more energy. Therefore, we say second ionization energy is more than first ionization energy. Suppose you have removed second electron also. Now, how many electrons remained? I'll give you simple example. These examples need a different understanding. Yes. So here I'll give you example of some metal atom, say it is having 10 electrons. So I will put first ionization energy and I will remove one electron. So here how many electrons came? 9. So for this I will put second ionization energy and it will become m plus 2. How many electrons are there? 8. Here I will put third ionization energy and I will remove one more electron. It becomes m plus 3. How many electrons are there? 7. So when you are putting energy in stepwise, what is happening? Number of electrons are decreasing. As number of electrons are decreasing and nuclear attraction is the same, it is not changed. So what happens here in case of this unipositive cation, the nuclear attraction has to get distributed to 9 electrons now. So new effective nuclear attraction on remaining electrons increases. So when nuclear attraction on remaining electrons increases, can you remove the electron easily? No. Therefore, whatever second ionization energy you are putting to remove the second electron, it will be more than the first ionization energy. Now, once you removed the second electron also, how many electrons remained? The number of electrons is again decreasing. The nuclear attraction on remaining electrons is still more. So it still becomes more. Here there are 10 protons. It is attraction on 10 electrons. Here still there are 10 protons. Attraction is on 9 electrons. So nuclear attraction increased. Here there are still 10 protons, attraction is on 8 electrons. So nuclear attraction has still increased. Yes, here when there are 7 electrons, still 10 protons, nuclear attraction has still increased. So as number of electrons go on decreasing, nuclear attraction on remaining electrons increases. Thus the successive ionization energies go on increasing. Therefore, we say the fourth ionization energy is greater than the third ionization energy, which is greater than second ionization energy, which is greater than first ionization energy. It is let it for any of the elements, the successive ionization energies will be more, because as the number of electrons are lost, the nuclear attraction, the number of electrons decrease. As the electrons are lost, the number of electrons decrease. When the number of electrons decrease, the nuclear attraction on the remaining electrons increases. When nuclear attraction increases means what? Electrons are held more strongly. That time you need to put more energy to remove the electrons, in order to remove the electrons. Understanding? Therefore, what happens? The successive ionization energies I1, IE1, IE2, IE3, IE4 are called successive ionization energies. There will be increase in the successive ionization energies. That is, the energy required to remove fourth electron will be more than the energy required to remove third electron, which will be more than the energy required to remove second electron, which will be much more than the energy required to remove first electron. And these energies, they vary. How much more? It depends on the element. Yes, how much more it depends on the element. But in general, this is always followed. The successive ionization energies are always more. What energy you need to remove first electron, what energy you need to remove second electron, what energy you need to remove third electron, what energy you need to remove fourth electron. It varies like this. The energy needed to remove second electron is more than the energy required to remove first electron. The energy required to remove third electron is more than the energy required to remove second electron. The energy required to remove fourth electron is more than the energy required to remove third electron. So it increases. So we have understood what is ionization energy, how it varies for different elements. I will discuss it. That is also there. This exactly, it is not followed the same. Yes. So how it varies for different elements, I will discuss it. So what is ionization energy? Minimum amount of energy required to remove an electron from the isolated gaseous atom in its ground state. So gaseous atom is there. You apply certain energy called ionization energy, electron is lost. The unit of ionization enthalpy is, it is energy, right? So kilojoules per mole. Means what? The minimum energy required to remove electrons from 1 mole of neutral gaseous atoms. And unit of ionization, if it is said ionization potential, it is electron volt per atom. Successive ionization enthalpies. If a gaseous atom is to lose more than 1 electrons, they can be removed one after the other, that is in succession. You cannot say I will remove all 4 electrons at a stretch. No, one after the other. First electron, outermost shell electron has to be lost. Then the next inner shell electron, then the next. So it has to be removed one after the other, that is in succession and not simultaneously. This is known as successive ionization enthalpies. They have shown here. So ionization enthalpies required to remove first, second and third electron from gaseous atoms are known as delta IH1, delta IH2, delta IH3, or I can, as I said, we can represent them as IE1, IE2 and IE3. Yes, here example of aluminium is shown. So aluminium, remove one electron, it is Al plus. So this is IE1. So this is what? This is IE1. Aluminium ion is there. You want to remove one more electron, IE2. So you'll write IE2. Aluminium plus 2 ion is there. Apply energy. It will form IE3. Yes. So look at the energies. First electron, to remove the first electron, I need 577 kilojoules per mole. For second electron, 1816 kilojoules. For third electron, 2744 kilojoules of energy. Yes. So IE3 is more than IE2, which is more than IE1. Yes. And how this ionization energy varies for different elements, we are going to discuss it in the next class. Hope you have got cleared with the concepts of atomic radius, variation and ionization energy some part. Next variations we'll be discussing in the next video. For now, thank you.